We have learnt that the ideal gas equation describes the behavior of gases based on experimental observations. To understand the behavior of gases at the molecular level, scientists developed a theoretical model called Kinetic Molecular Theory, KMT, or Microscopic Model of Gases. Kinetic molecular theory is a set of 5 assumptions that describes the behavior of molecules in a gas. Let's discuss the assumptions and how they are justified in detail. Gases consist of very large number of extremely small particles called molecules, which are in constant, continuous, random and straight line motion. During their motion, they collide with each other and against the walls of the container. The pressure exerted by the gas is due to the bombardment of its molecules on the walls of the container. The molecules of a gas are separated from each other by great distances. Hence, the actual volume of all the molecules of the gas is negligible when compared to the total volume occupied by the gas. This assumption is true as gases are highly compressible. Hence, the actual volume of all the molecules of gas is negligible. Attractive and repulsive forces between the molecules of a gas are negligible as they are much away from each other. We can state that assumption 3 is true as gases expand and occupy the entire space available to them, showing the existence of weak intermolecular forces of attraction. Hence, attractive or repulsive forces between the molecules of a gas are negligible. Individual molecules do not gain or lose energy as a result of collision. Therefore, collision between molecules is perfectly elastic. This assumption can be justified because during collision, the molecules do not settle down or slow down. The average kinetic energy of the molecules is proportional to absolute temperature. Assumption 5 is the result of the fact that when the temperature of a gas is raised, the molecules start moving faster. Thus, their individual kinetic energies increase and hence the average kinetic energy increases. Based on these assumptions, an equation for pressure of a gas is derived as PV is equal to 1 by 3 mnu square. This is called the kinetic gas equation, where n is the total number of molecules in volume V, m is the mass of the gas molecule, and u is the root mean square velocity of the molecules. Let us now understand the gas laws in terms of the kinetic molecular theory of gases. First, let's start with Boyle's law. Consider a given amount of a gas in a cylinder fitted with a frictionless piston. According to kinetic molecular theory, pressure exerted by a gas is due to molecular collisions on the walls of the container. As the number of collisions increases, the pressure of the gas also increases. The average velocity of molecules is constant at a given temperature. When the volume of a gas is decreased, the space available for the movement of molecules decreases. Then, the number of collisions on the walls of the container increases, resulting in an increase in the pressure of the gas. This means, as the volume of a gas is decreased, pressure is increased for a given mass of a gas at a given temperature. This is Boyle's law. Next, let's take a look at Charles' law. Consider a given amount of a gas at normal atmospheric pressure enclosed in a cylinder fitted with a frictionless piston. When it is heated, according to kinetic molecular theory, the average kinetic energy of the molecules increases. Then, molecular velocities increase, thereby increasing the number of collisions with the walls of the container as well as the momentum of each molecule. As a result, the piston is pushed outwards. The volume of the gas then increases. Hence, at constant pressure, when the temperature of a given mass of a gas is increased, its volume increases. This is Charles' law. Next, let's move on to Avogadro's law. Consider equal volume of two gases under the same conditions of temperature and pressure. Since the temperature of the two gases is the same, according to kinetic molecular theory, the average kinetic energy of the gas molecules should also be the same. We know that the pressure of a gas depends on the number of molecules present per unit volume, as well as their average kinetic energy. As the two gases have the same pressure and same kinetic energy, they must have an equal number of molecules per unit volume. This means equal volumes of all gases under similar conditions of temperature and pressure contain an equal number of molecules. This is Avogadro's law.